everybody and welcome to another video. In today's video we'll be walking you through, or I will be walking you through a C++ translation of QuickSort recursive function into Goto Labels. So this translation is solely going to be based upon the translations we've made in the past, such as sum binary tree, print binary tree, all of which can be found on this channel. Just look for the keyword recursion in the title and you will find all of the respective videos to get you up to speed and up to date with what we are doing here today. So yeah, I just said that because there is a lot of videos on recursion on this channel. So just look for the word or keyword recursion or clue word recursion in the title and you will find it. Alright, so what's really interesting, and I'm not gonna walk you through the semantics and the logic of the QuickSort algorithm, we're just going to replace the recursion call with the Goto labels as we've done in the previous videos. So this function I took from GitHub, and kudos to this person who implemented it in C++. Or actually C, so I just transferred it to C++ because we have static storage implementation that we can use for our stack, etc. So I do prefer sort of just having a C++ version of everything, so we're more flexible in using all sorts of containers. But if you want to use C purely, we can make another video of that as well. So the function is relatively simple. You do a partition here, and then you have two recursive calls which we are going to turn into Goto labels. So as you already know, in other videos our call frame was based on the function arguments, on the return value, and in this case QuickSort is void, so we will have no return values, only the call of the origin, or the origin of the call rather. And that really makes life easier for us on that side of things. And this is something that I haven't talked about in previous videos, and that is the body of the function. In case you have a while loop in your recursion, how do I translate that? That depends on a variable that's defined in the body or in the function arguments, and in which case we have the low and high. And also I have another translation that I've made, and it's in the GitHub repository named C++, or is it C++? One second. Okay, there we go. Recursion into labels part 3. Yeah, it's here, and if I take a look at that file, I made a simple translation of, or rather a translation of the simple recursion call where we have a for loop in there. And I also here made sure that I use volatile so that my for loop doesn't get turned into, if I say something like this, right, my loop is going to be removed, then I will have these three, which is a great compiler decision, but I wanted to avoid that for cleaner assembly, and so that it is easier for me to make that translation. So essentially our and needed to be defined in the middle of the function. In order to have that in your call frame, you would need to have the body variables, and this has to be, and sort of the crux of the matter here is the evaluation. I cannot simply evaluate this variable anywhere else. Let's say if it's an expression and the evaluation order matters to us, or the evaluation precedence, I have to make sure that it's put in the middle of the body, just as here. And if you turn, and what I'm talking about is the int 1, and when you turn that into a while loop, and that's why I turned this into a while loop, because it's easier to translate now into a recursion or Goto labels, I would select my current call frame, my current function call frame, and reference that, or evaluate, or now let's say declare that variable where I'm evaluating the initialization in the right order, and that's absolutely gonna cut it for me, and that's it. So that's why this body variable is important, and something that we haven't covered in the previous videos, or we didn't cover in the previous video, but now that we are covering it, you can say we haven't covered it. So that's the call frame logistics. And now if we get to actual translation, this is not gonna be so much different from our previous translations for printing a binary tree and summing up the binary tree, or getting the sum of the binary tree, in other words. So essentially we have the first call, which is going to be the first push. And also what's important to note is that if you look at the assembly translation, you will see that we have first push. This push is most likely to be the call, or the first argument of the QuickSort here. And that's going to be array, low, and high. And for us, by the way, we have another push, and that is for pushing the body variables. So that's why I commented here push variables. And now we move on to the actual, we call the partition. That is fine. I made sure this is inlined. If we go to the definition and the declaration, I made sure that it's inlined at all times for performance sake. And you would want this to be inlined because you want to perform quick sorts, as as the name itself suggests, after all. So then we have this call here that we're trying to make, and we are essentially going to initialize the first argument, function argument, the second and the third, which is going to be pi minus 1. And then we have to make sure we point to that function origin. We push the call via static storage that we've implemented a while ago, and make sure to check out the video called C++ static storage implementation to get you up to speed. And we have the origin of the return, which is quite straightforward based on all the videos that we made up to this point. And then we get to something interesting, and that is accessing the PI, and that is the variable that we were trying to define in the function body. And if we comment this out, by the way, we are gonna get, now all the tests will pass, as well as our fuzz tests, so there's no question about it. But I just simply don't like this code, because my PI is based here, and once I'm jumping via indirect jump to my function called oneOrigin, I wouldn't know where is my PI. PI would be fine to be somewhere in here, but that's not our code logic in the first place. It's fine when you need to access it as a global variable. So let's say I'm accessing it here. PI, the compiler will turn this into something like move rbx minus, let's say, 16. Where if we define it here, this is going to be move rbx minus 8, let's say. So you can see that the more we go try to get out of the nested scope or try to read a variable that's defined in the higher scope, the compiler will simply access it as something out of that scope and would have no problem with it whatsoever. But since this is not our function logic and our code logic, we cannot do that. So in order to refer back to our PI, and you'll see in the compiler, once we compile this code, oh, I have a lot of fuzz tests, right? Let me just, I will have to comment these out for us to see that warning error. Am I compiling? Yeah. So yeah, I'll have to comment that out. Okay. And the compiler itself warns you this may be initialized, like we just talked about. Because it's not, while it is technically in the outer scope, it's still not guaranteed to be what we expect it to be. And yeah, now we'll be fine. So that's how you would access your variable here. When you're using recursion in purely as typical recursion, and you write your code normally, but not like me, this is not a problem at all. You would just access it like this, and that's it. You take all this stuff for granted, in other words. But if you want to access it in the current call frame, it will be the last element of your stack. That's where the PI will be, behind the scenes. Because once we call this function, we're in the current call frame, right? And we access PI. But once we return out of it, we still need to access the PI. How do we do that? Still the same logic. The current call frame, which is the last item of our call frame stack. And that's it. And then we have pretty standard stuff here where we pop our call of the stack, and this will be this call right here. Once we push, we pop it out of the stack, and if we are finished with executing our recursion, that's it. We jump to done, and since we are not returning anything, we're just gonna say return and return from a void. So I've also written a bunch of tests because I'm paranoid and I want to be 100%, 100% sure that I'm writing accurate and correct code. So we have run tests here where we are on heap allocating a lot of arrays and we are using the built-in function in C that's defined in the stdlib header in order and that's gonna be the guarantee for us whether or not we are sorting correctly. And then after that we have some fixed tests here, and to cap it all off and put the icing on the cake and put the finishing touches, we have the fuzz test. And now if we run all of that, we are all good. I use Valgrind to run like fuzz tests as well, because if I see a really huge big message, I'm like, okay, we blew up. Something in the code blew up at runtime, and that needs to be investigated. So you can see that we are sorting at the maximum accuracy. So to sort of wrap up the series of recursion being turned into Goto labels, I've decided to sort of take this really standard algorithm and write a bunch of unit tests to verify my theory. I mean, we did run a lot of tests with binary trees, but who knows, right? You can never be too sure. And now I'm pretty happy that this approach works, but the downside to it is that I wasn't able to make it faster than the typical recursion, because it's just CPUs are so advanced nowadays that all of these optimizations become obsolete almost. However, one use case where it wouldn't be obsolete or redundant is, or futile, trivial, whatever word you want to use, is a scenario where I need to grow my stack dynamically. So there's no way for you to write a recursion where you're gonna put your calls to be pushed and popped and returned onto the stack on heap. There is no such compiler option, nothing. So this would be the approach to take if you want to turn your recursive solution into dynamic based stack. For example, all you need to do is go here, say std vector, call frame, and do your stack. You have to do some modifications here, but I mean allocate your stack, but you have to do some modifications here as well to keep it up to date with what vector offers in terms of member functions, etc. And I would do reserve here just to try to predict what's gonna be my starting point of the stack. For example, if we are programming or we are using this approach for video games, where we expect for something large to be loaded into our video game, like a texture, like a level, and we would do 10k, a million, so we would do that kind of stuff by reserving the space. If we are 100% sure that, okay, I will never depend on reservation that's like 100, because my game will never load anything that's as small as 100. So you have to find your minimal value for that. But just to go back to the point, it's pretty difficult to outshine modern CPUs, because they're really optimized for scenarios such as call, push, and pop. But in the end, we have made, and I mean, this kind of stuff as well, this approach would take a toll on your data code base and the readability of it, really, and maintenance and all that kind of stuff. If you're not a crazy scientist or a mad scientist developer, something like this is, in other words, ill-advised and just bad. Alright, that'll be all for this video. Thank you so much for watching, and until next time, take care.